Have you ever wondered how your phone battery works? Or how a shiny metal object gets its coating? The magic behind it all is a fascinating branch of science called electrochemistry. It's all about the relationship between chemical reactions and electricity. Think of it as a bridge connecting the world of atoms and molecules with the world of electrons and currents. Today, we're going to dive deep into this electrifying topic, starting from the very basics and building our way up. So, grab your thinking caps, and let's get charged up about electrochemistry. First, let's talk about how electricity moves. We have two main types of conductors. You're probably familiar with the first one, metallic conductors. These are your everyday wires, like copper or aluminum. In these materials, electricity is simply the flow of electrons. The metal atoms stay put, while the tiny electrons zip through the material, carrying the charge. It's like a river of electrons flowing through a fixed channel. But there's another, equally important type, electrolytic conductors. This is where things get really interesting from a chemistry perspective. Instead of just electrons moving, we have ions, atoms or molecules that have gained or lost electrons, giving them a positive or negative charge. When we dissolve something like table salt, which is sodium chloride, in water, it breaks apart into positive sodium ions and negative chloride ions. When we apply an electric field, these ions physically move through the solution to carry the current. The positive ions move towards the negative electrode, and the negative ions move towards the positive electrode. This movement of whole ions is what constitutes the electrical current in an electrolyte solution. So what's the key difference here? In a metallic conductor, it's just electrons on the move, and no chemical change happens to the conductor itself. The copper wire remains a copper wire. But in an electrolytic conductor, the flow of current involves the movement of matter, the ions, and this often leads to chemical reactions at the electrodes. For example, we might see a metal plating onto one electrode or gas bubbling off another. Another big difference is temperature. For metals, increasing the temperature increases resistance, making them worse conductors. But for electrolytes, increasing the temperature usually helps the ions move more freely, making them better conductors. It's a complete flip. Now, let's focus on these electrolyte solutions. How does this conduction actually happen? Imagine a solution full of these positive and negative ions, all zipping around randomly. When we introduce two electrodes, a positive one called the anode and a negative one called the cathode, and connect them to a power source, we create an electric field. This field acts like a guiding force. All the positive ions, or cations, start migrating towards the negative cathode. At the same time, all the negative ions, or anions, are drawn towards the positive anode. This organized, two-way traffic of charged particles is the essence of conduction in an electrolyte solution. It's a beautiful, microscopic dance that allows electricity to flow through a liquid. Of course, not all electrolytes are created equal. We can broadly classify them into two categories, strong and weak. A strong electrolyte is a substance that, when dissolved in a solvent like water, completely or almost completely dissociates into its constituent ions. A classic example is sodium chloride. You put it in water, and virtually every single NaCl unit splits into a sodium ion and a chloride ion. This means there are a lot of charge carriers available, making strong electrolytes excellent conductors of electricity. Other examples include strong acids like hydrochloric acid and strong bases like sodium hydroxide. On the other hand, we have weak electrolytes. As the name suggests, these substances only partially dissociate into ions when dissolved. A great example is acetic acid, the main component of vinegar. When you dissolve acetic acid in water, only a small fraction of its molecules break apart into hydrogen ions and acetate ions. Most of the acetic acid remains as intact, neutral molecules. Since there are fewer ions available to carry the charge, weak electrolytes are poor conductors of electricity compared to strong ones. This difference between strong and weak electrolytes is crucial for understanding many chemical processes, from the pH of a solution to the efficiency of a battery. Now, things in chemistry are rarely as simple as they first appear. In a solution, ions don't just exist in a vacuum. They interact with each other. These interactions can affect how they behave. To account for this, chemists use a concept called activity instead of just concentration. You can think of activity as the effective concentration of an ion. It's a measure of how an ion feels. and reacts in the presence of all the other ions around it. The link between the actual concentration and this effective concentration is a value called the activity coefficient. It's a correction factor, usually less than 1, that tells us how much the ion's behavior deviates from the ideal. For a very dilute solution where ions are far apart, the activity coefficient is close to 1, and activity is almost the same as concentration. So what factors influence this activity coefficient? What determines how much the ions interfere with each other? One of the biggest factors is something called the ionic strength of the solution. Ionic strength is a measure of the total concentration of ions in a solution. The higher the ionic strength, meaning the more crowded the solution is with ions, the more they interact and shield each other from the electric field. This increased interaction lowers the activity coefficient, meaning the ions behave less ideally. It's like being in a crowded room. It's harder to move around and do your own thing compared to when you in an empty hall. The ionic strength depends on both the concentration and the charge of all the ions present. Another important factor is the size of the ion itself, specifically its hydrated radius. When an ion is in water, water molecules are attracted to its charge and form a shell around it. This whole package, the ion plus its water shell, is what actually moves through the solution. This effective size is called the hydrated radius. Smaller, more highly charged ions tend to attract more water molecules, sometimes giving them a larger hydrated radius than you might expect. This size affects how easily the ion can move through the solution and how it interacts with other ions, thus influencing its activity coefficient. Finally, and perhaps most obviously, the charge of the ion itself plays a huge role. An ion with a higher charge, like a calcium ion with a +2 charge, will have a much stronger electric field around it than an ion with a +1 charge, like a sodium ion. This stronger field leads to much stronger interactions with other ions and with the solvent molecules. These powerful interactions cause a significant deviation from ideal behavior, resulting in a much lower activity coefficient for more highly charged ions, especially as the ionic strength of the solution increases. It's a key reason why a solution of magnesium chloride behaves so differently from a solution of sodium chloride, even at the same concentration. Understanding these factors is key to accurately predicting and controlling chemical reactions in solution. And that's our deep dive into the fundamentals of electrochemistry for today. We've journeyed from the basic idea of electrical conductors to the complex world of ion interactions in solution. It's a field that powers so much of our modern world. I hope this has sparked your interest. If you found this video helpful, please give it a thumbs up and don't forget to subscribe and hit that notification bell so you don't miss our next electrifying adventure into science. Thanks for watching and see you in the next video.